Today, we're diving into a really fascinating proposal from researcher Kevin L. Brown. It's an idea that looks at gravity not as some unchangeable law of the universe, but, well, as an engineering problem that we could potentially solve. So let's start with a big question, a really powerful one. I want you to just forget everything you think you know for a second about mass and weight. What if the force that's holding you in your chair right now isn't some fixed cosmic rule? What if it's more like a dial, a setting, that we could actually learn to adjust? To even begin to answer that, we have to start by rethinking inertia. You know that feeling when a car suddenly accelerates and you're pushed back in your seat? For hundreds of years, we've basically treated that as a fundamental, unchangeable part of reality. But what if we've been looking at it all wrong this whole time? And here's where the two ideas really split. On one side, you have the standard view, the one we all learn in school. It says that mass is just an inherent part of an object. It is what it is. But this informational view proposes something wild. It says inertia isn't in the object at all. Instead, it's the result of how strongly that object is connected or coupled to a universal information field, kind of like a hidden data layer that underpins all of reality. So what does that coupling actually feel like? Well, the best way to think about it is like drag. Imagine moving your hand through a pool of water. You feel that resistance, right? This theory suggests that inertia is basically the same thing. It's an informational drag that every single object feels as it moves through this field. So the more connected an object is, the more drag it has, and the more massive it seems to be. And this, of course, leads to a pretty thrilling question. If inertia is just a type of drag, well, could we find a way to reduce it? Could we actually engineer something to be more slippery as it moves through this informational field, to, in effect, lower its mass without changing the object one bit? The proposed answer is a technology with a bit of a mouthful of a name: Phase-Coherent Inertial Modulation, or PCIM for short. So let's just break that down. It's basically a fancy term for a mechanism that's designed to actively tune or modulate an object's connection to that information field. The idea is to give us direct control over its inertia. Now, this isn't just a vague concept. It's a real engineering proposal, and it has very specific targets. For this whole thing to be genuinely useful, the research says we need to hit a 50 to 95% reduction in an object's effective mass. That's the sweet spot, the optimized range, where the real-world applications start to become absolutely revolutionary. Let's really try and picture what that 95% number means. Imagine you have a solid 100-pound object in front of you. With this tech switched on, it would still be the exact same dense, solid thing, but it would feel like it only weighed 5 pounds. You could just pick it up with one hand. That's the goal we're talking about here. So how in the world would this actually work? The proposed PCIM process has 4 main steps. First, you stabilize the object's atomic structure. Then you harmonize it using a very specific electromagnetic field. The third step is to align something called its reflectivity index. You can think of that as the dial that controls how much drag the object feels. And the final result? The object's connection to the field weakens, and it starts to behave as if it has a whole lot less mass. Okay, I know, this all sounds like it's straight out of science fiction, but any good scientific theory has to be testable. You need a clear experiment that can prove it's right, or, and this is just as important, prove it's wrong. And that brings us to what's called the falsifiable drop test. And the beauty of this test is just how simple it is. You take 2 identical 100-pound spheres. Sphere A is your control, you don't do anything to it. But sphere B has the PCIM technology turned on, aiming for that 95% mass reduction. Then you just drop them both from 100 meters high, and you watch very, very closely to see what happens. And here is the absolute crucial part. The theory predicts that sphere B, the lighter one, will actually fall at the exact same speed as sphere A, 9.8 meters per second squared. Gravity is still gravity, but its impact force when it hits the ground should be tiny, like a 5-pound object hitting the ground. And this is the key to good science, the falsification part. If sphere B slams into the ground with the force of a full 100-pound object, then the whole theory is just plain wrong. The effect is an illusion, and it's time to go back to the drawing board. But what if the theory is right? What if that drop test works exactly as predicted? Well, then the implications are absolutely staggering. We're not just talking about a new gadget. We would be walking into a completely new chapter for humanity. A truly weightless future. Just think about the applications. A weightless logistics chain could let us move 100-ton shipping containers using the same energy it takes to move a car. We could save buildings and bridges during an earthquake by temporarily making them almost weightless. Space travel could be revolutionized by sliding through the atmosphere instead of using brute force rockets. We could completely redesign our cities, building vertically without the same massive structural limits. It would change everything, to the point where moving heavy things around is no longer the main energy cost of our entire civilization. Which brings us right back to where we started. This proposal totally reframes our relationship with the physical world. It suggests that if we get a deeper understanding of how information and reality are connected, one of the most fundamental forces in the universe might just become another variable we can learn to control. The question it leaves us with isn't really if we can, but what happens to all of us when we finally do?